How can you make math easier, and also more fun, for children? Isn't math just about facts and skills, and about doing them, or stating them correctly? Math is also about concepts, and the development of these concepts depends on the development of powerful models for interpreting experiences mathematically. So, what are these model-based concepts, and how can we help children develop the models that are needed? Consider the following examples. Have you ever asked someone for directions in a large zoo or park, or in a new town, or on an unfamiliar college campus? Have you ever misunderstood what they were saying or showing because you failed to notice some important information, or because you made assumptions that were not appropriate? One important way that people interpret information, and one way they organize it so they'll remember it later, is by using internal models, or frameworks, or maps. Similar things often happen when children hear math facts, or see math procedures, in complex situations like the one shown here. Of course, this situation is more complex than kindergartners encounter. But the point is that, in demonstrations and explanations that children encounter in school, what they see, hear, and understand depends on conceptual systems, or models that they develop to organize and explain what they are seeing or hearing. And, for the situation shown here, important parts of the interpretation systems begin to develop in kindergarten. So, kindergarten math isn't just about counting and calculating. It's also about seeing and describing things mathematically. To see what this means, consider the display of dots shown here. What do you see? Perhaps you only see 7 dots, or perhaps you see these dots as being organized in a circle, or perhaps you see 6 triangles inside a shape that looks like a stop sign. But now what do you see? Probably a cube. But you know that the cube isn't really in the information that is given. You're attributing cubeness to what you see because of the way you're organizing the information you've been shown. And what you end up seeing comes as much from the system that you impose on the information as it does from the information itself. In fact, in this display, it's possible to see 6 different cubes. And once you've seen one or more of these cubes, it's difficult to remember what it was like before you saw them. Similar things happen in many hidden picture puzzles. For example, in this picture, it's possible to see either a young woman or an old woman. And again, once you've seen these pictures, it's difficult to remember what it was like before you saw them. Other examples similar to these are easy to find. If you conduct a Google search for perceptual illusions, for example, here is one such site. Even though many people refer to these kinds of situations as perceptual illusions, most of them occur because of the ways that the figures are conceived, not simply perceived. In other words, if you think about things differently, then you see different things. To see another example of how conception influences perception, imagine flashing up this picture for a friend. Then, hide the picture, and ask your friend to draw a picture of what they saw. This probably will be quite difficult, because the picture probably won't fit familiar patterns that most people have developed to make sense of experiences. Yet, the picture is not complex. So, poor drawing abilities is not why it's difficult to draw. It's because the relationships in the picture don't fit models which are built on prior experiences. The kind of examples you've just seen were first studied by early Gestalt psychologists. A Gestalt is a situation in which system as a whole has meanings or properties that go beyond those of its parts. Such systems are common in fields ranging from economics, to physics, to music, where patterns often have characteristics that go beyond those of isolated pieces. But, whereas fields like economics, and physics, and music are concerned with the economic, or physical, or musical properties of these systems, Mathematics is about the structural or systemic properties of systems. So, students who develop models that use these systemic properties to conceptualize things are able to see mathematical patterns and regularities that other students don't. For young children, similar things happen for many situations that involve mathematical thinking. This is because mathematical concepts almost always involve patterns and regularities that must be imposed on situations, rather than simply being extracted from them. So, for adults who have already developed relevant models, it's often surprising that children don't see the same things that we see in math-related situations. For example, in this task, a primitive response might begin with the child starting to make a one-to-one match between yellow counters and red counters. But, when attention focuses on putting out one counter at a time, young children often lose sight of the overall goal of making a 3x3 array. So, they end up making a configuration that looks something like this. When their attention centers on the whole, they confuse the parts. And, when their attention focuses on the parts, they confuse the whole. So, in general, they have difficulty thinking about wholes and parts at the same time. Even if they succeed at making a 3x3 array, they may get confused if you move the counters in one configuration so that part-whole relationships are less clear. If you point out that all you did was to rearrange the red counters, without adding any or taking any away, preschoolers are still likely to believe that the two collections no longer have the same number of counters. Adults may look at these collections of counters and see a configuration with 3 rows and 3 columns, or 3 subsets of 3. But, this may not be what preschool children see. In fact, if you count the red counters, and say, "There are 9 of my red counters, how many yellow counters do you have?" Many preschoolers are likely to guess 8, or 10, or anything but 9. In fact, even if you ask such children to count the number of counters in their collection, they are likely to skip some counters, or count other counters twice, and often end up with a count that fits with their prior assessment that the two collections aren't equal. See what's going on here? Consider another similar task. This time, put marbles into 2 different shaped glasses as shown here, and, each time you put a marble into your cup, ask the child to put a marble into his, and, to count the marbles as you go. Then, after putting 8 to 12 counters into your cup, remind that child that, each time I put a red marble in my cup, you put a yellow marble in yours. So, there are 9 marbles in my cup, how many marbles are in yours? Many preschool children will center on only the height of the marbles in the 2 cups. So, they may guess that there are more red marbles than yellow marbles, even after they have been reminded that the marbles were matched 1-to-1 as they were put into the 2 glasses. What's going on here? Consider the following example. Put 3 different colored mountains on a table as shown here. Then, ask a preschool child to walk around the table and, at several different locations, to select from a set of photographs the one that shows what they see at that location. As a primitive response, a preschool child might center their attention on the mountain that is closest to them, but not pay attention to the locations of the other 2 mountains. So, they might pick the bottom left photograph, rather than the bottom right photograph. Furthermore, even later, when the child pays attention to the relative locations of all 3 mountains, you can ask them to sit in one location, and to choose the photograph that shows what a toy bear sees from another location. And, the photograph that the child picks may again be the one showing what they themselves see. Young children's thinking is often conceptually egocentric. They have difficulty imagining the perspectives of others, and, in fact, they may even have difficulty imagining their own perspectives at some other point in time. So, they often have difficulties explaining their thinking to others, or imagining any interpretation of a situation but their own, at the moment. And, When their thinking is conceptually egocentric, they tend to be even more inclined to center their attention on only a few isolated pieces of information, rather than recognizing patterns involving more information. Here's another example that illustrates some common characteristics of children's early systemic thinking. Put out a row of sticks in a stair-step configuration, as shown here. Then, mix up the sticks and ask a preschool or kindergarten child to rebuild the row of sticks, just like they were before. A primitive response to this task often starts by picking a short stick, which is not necessarily the shortest stick, and then picking some other longer stick. Then, the child may continue to pick more short-long pairs, until all of the sticks are gone. Or, here's a bit better coordinated response to this task. But, the child still ends up with several subsequences. What such responses reveal is the difficulty that young children often experience when they try to choose a shortest stick followed by a longer stick that is shorter than all of the other sticks, and so on until all of the sticks are gone. In other words, such children are having difficulty coordinating shorter than and longer than relationships, or less than and greater than relationships. Consequently, even if the child succeeds in reconstructing a stair-step arrangement of sticks, they may have difficulty knowing where to put a new, missing middle-sized stick, because doing so would involve thinking simultaneously about bigger than and less than relationships. So again, when a child's thinking about such systems of relationships is not well coordinated, they are likely to center on one piece of information, such as the tops of the sticks, and neglect to notice other important information, such as the bottoms of the sticks. In this sense, uncoordinated operational relational systems behave similarly to uncoordinated systems of physical actions, such as those that are involved in riding a bicycle or hitting a tennis ball. When relevant systems as a whole are not functioning in a well-coordinated ways, then it's difficult to notice more than a few fragmented pieces of information, and it's also difficult to think of anything that is not immediately in front of you at the time. So, if children have difficulties coordinating part-whole relationships, part-part relationships, and ordering relationships, then systemic thinking that depends on these relationships is likely to involve both conceptual centering and conceptual egocentrism. So, young children may not see things the same ways that adults do in many early number tasks. But, these are not just cute characteristics that only apply to the thinking of young children. For more complex types of systemic thinking that occurs beyond primary school mathematics, these characteristics also apply to older students or adults. To help you better understand some of the early systemic thinking of young children, here are several adult-level tasks that are similar to some of those we've shown for children. This figure shows a string of 32 red beads surrounding a game board, which has 64 spaces, 8 rows and 8 columns. Now, let's move the string. And, notice several facts. First, the string of 32 red beads has not changed, and, just as in the number tasks that we showed for children, we could undo what we just did. So, how many spaces should now be enclosed inside the string? If you guessed 64, then watch as we continue to move the string. In the end, it's clear that the number of spaces was not preserved under these transformations. In fact, after the very first step, there were 7 rows and 9 columns. So, there are only 63 spaces. We lost 1 space in the very first step. What this shows is the not very deep fact that whenever you change something, something changes. And, something else does not change. So, for this task, how could you know that the area enclosed within the loop of string is the thing that changed, and it was the perimeter that did not change? But, the simple fact that you could undo what you did doesn't prove anything. So, if this explanation doesn't make sense to a child, then they are right to be skeptical. Here are 2 more examples. First, cut the shape into a small number of parts. Then, rearrange the parts. In the first figure, there were 64 spaces in the game board. So, how many spaces are in the new game board? Again, the answer is not 64. So, what happened this time? If you look at the game board carefully, you can see that the cuts were cleverly made so that the old spaces were no longer all the same size. In other words, part-part relationships changed. And, if you look carefully at the second figure, then you'll see that the cuts were again cleverly made so that the two whole figures are no longer exactly the same. So, part-whole relationships changed. Just as in the earlier examples of number tasks for children, the concept of area that is needed in this game board task involves a system of relationships and operations involving parts and wholes, and parts and parts. Sometimes it's possible to use some trick, as we did here, to lure adults into engaging in appropriate systems of relationships and operations to interpret the situation. But, for young children, they may have not yet developed the appropriate system. Let's look at an example where there are no tricks. Begin by showing how all of the counting numbers in the world can be listed. This is simple, and the ... at the end means the pattern continues for as long as anybody wants it to continue. Next, let's use a similar method to show how all of the fractions in the world can be listed. First, make a row of all of the fractions with 1 in the numerator. Then, make a row for all of the fractions with 2 in the numerator. And, continue this pattern for as long as anybody wants us to continue. So, using this method, it's clear that no fractions will be missing. And, here's a method that can be used to count them. Again, notice that every single fraction will be counted using this method. And, this means that we just made a one-to-one correspondence between the counting numbers and the fractions. But, you also know that between any two counting numbers, there are many fractions. So, do you really believe that there are the same number of counting numbers as fractions? Remember two facts. First, we just counted them. Second, we matched them one-to-one. If you still don't believe that there are just as many counting numbers as fractions, then I'm afraid that you're wrong. In fact, if you became a university mathematician, then you'd see that we just gave the most widely used proof that there are the same number of counting numbers as fractions. You may be saying to yourself, I don't care if you just counted them and matched them one-to-one. If you look at them on a number line, then you can see that there are lots more fractions than counting numbers. And, if this is what you're saying, then perhaps you'll have a bit better understanding about why a young child might give the responses that they do for tasks like those we've shown. But, whereas you might need more experience with infinite sets of things, young children often need more experiences with finite sets. This video began with two questions that have closely related answers. First, how can I help make math easier and more fun for my child? Second, isn't math just about facts and skills? What this video has tried to show is that, first, math is also about concepts. Second, conceptualizing things mathematically means thinking about them systemically. That is, interpreting their meanings using systems of relations and operations. Third, mathematical interpretations depend on the development of models for describing, explaining, or developing the relatively small number of elementary but powerful systems that underlie all of elementary mathematics. For young children, some of their most powerful models for describing and explaining things are embodied in meaningful stories, accompanied by math-evocative objects, which provide contexts for refining useful language and inscriptions. So, the activities that accompany these videos are designed to help young children develop simple but deep models for some of the most important kinds of systemic thinking that will be useful to them in early mathematics activities in school. For example, one of our first stories is about Beauregard Frog and proper hops for all frogs in Sugar Swamp. These children are practicing proper hops and investigating distances between points. One kind of problem is, where should Beauregard's lily pad be located, so that the sum of distances to his three friends' lily pads is as small as possible? But, Before trying to solve this problem, you might want to begin with a few warm-up problems. Also, if your goal is to understand how children are thinking about these kinds of situations, then it usually is useful to have them work in groups of 3, so that thinking won't just happen in their heads, or so that what goes on in their heads will be more likely to be apparent in the language, actions, and notations that they use to communicate with each other. Activities about proper hops usually begin with a poster-sized picture like this, showing all of the lily pads in Sugar Swamp. And one good warm-up activity begins by marking one pad with an X, which shows one place where Beauregard might live. Then, another black dot or marker can be used to show a lily pad that is exactly 5 hops from Beauregard's pad. Then, the children's task is to mark other lily pads that are also exactly 5 hops from Beauregard's pad. Here is a picture that shows all of the pads that are 5 hops from this particular home for Beauregard. So, after children have finished this activity, it can be repeated by moving Beauregard's pad to a new location, and by asking for all of the lily pads that are exactly some other number of hops from Beauregard. A second activity begins by showing lily pads, marked A and B, where 2 of Beauregard's friends might live. Then, another marker or black dot shows a lily pad that is exactly the same number of hops from both A and B. For example, this particular point is exactly 5 hops from both A and B. Your children's task is to mark more points that are also the same number of hops from both A and B. Here is what the results should look like for these 2 locations for A and B, but you can move points A and B and similar patterns will occur. A third activity begins by showing where 3 of Beauregard's friends might live. Then, your children's task is to find a location for Beauregard's home so that the total of the distances to his 3 friends' pads will be as small as possible. If children write on each lily pad to show the total distance to points A, B, and C, then one kind of pattern that children may notice is shown here. The distances form a diamond-shaped pattern. Or, another pattern can be seen by drawing 3 horizontal lines through the points A, B, and C, and by making the middle line a different color than the top and bottom lines. Then, draw 3 vertical lines through A, B, and C, and again, make the middle line a different color than the other 2. The place where the 2 middle lines meet will be the place Beauregard should choose as his home lily pad, because this point is the one that minimizes the sum of the distances to the lily pads A, B, and C. To help children develop more generalizable and transferable knowledge from these kinds of proper hop activities, it is useful, at the end each activity, to help them write a short letter to Beauregard explaining to him, for example, where to locate his home so that the total of the distances to his 3 friends' pads will be as small as possible. Notice that, in these proper hop activities, children will be integrating ideas about numbers of hops, locations of lily pads, lengths of paths, and patterns involving multiple solutions to a task. Furthermore, they also will be investigating information about several paths. So, don't expect children to think about all of this information systemically at the start. Integration should be expected to take some time. So, what kind of math knowledge do children need to develop, beyond just facts and skills? Concepts and models for conceptualizing situations mathematically. To see the story about Beauregard and proper hops in Sugar Swamp, go to the YouTube site for Professor Arlesh and run the video called The Proper Hop.